Good morning. Welcome to the Future Internet course. This week is going to be composed of two different topics. First, an introduction to SDN, and then we will go to the difference between the control and data plane in SDN. And so first, we're going to see a couple of videos of the introduction to SDN. In the agenda, we will talk about why SDN is important, what is actually SDN, and which are SDN implications. The material taken from this slides that you can actually find online is a talk from Scott Schenker in UC Berkeley, another talk very important from Nick McCune in the Open Networking Summit 2011, and a document of Marco Sello from the University of Genoa. So you can actually find these resources online. So let's start a little bit. So first, we're going to talk about why. So why SDN appeared, or what are the reasons of SDN, or what is the motivation of SDN? And the thing is that we can see networks are really hard to manage. And when we say hard to manage, this is very important because now computation and storage are virtualized, right? So networks right now have to couple in the cloud with a lot of virtual machines, and they have to direct the information from one virtual machine to other virtual machine, and now the virtual machines are constantly changing, and they can be in one place, and the same virtual machine can be in another place, and then you have to redirect all the traffic in the network. So this is difficult to manage. And the infrastructure of the network have basically not changed during the past, I don't know, 20 or 30 years. So networks are very inflexible, still very inflexible and hard to manage. If you go to real networks, right, to the operating ones. The other thing is that they are very hard to evolve. So it's very difficult to innovate or to do new things in the network. Innovation, new languages, or new operating systems or applications are very difficult to apply. If you see the network manufacturers, the more general ones, Cisco, Juniper, and so on, they have the same interface, which is a OS system for networks that is proprietary and based on the standards. They just modify the system when a new standard arrives, which takes a lot of time. So if you want to put a new feature in the network, it's very difficult. It's very difficult to make innovations. Routing algorithms change very slowly. They are actually based on the standards RFC that are appearing, but this takes a lot of time. So it's very difficult to have new routing protocols in place. If you see, we are working still in intra or inside autonomous systems with OSPF, the same protocol as we have had for a lot of time, or MPLS, which is becoming old because it was defined at the end of the 1990s. So it's very difficult to innovate in terms of routing protocols. Network management is still very primitive. So what we do is we configure actually routers, boxes, routers, switches, and so on via these operating systems using commands, or these commands are dependent on the manufacturer. So it's very primitive what we do in terms of configuration in networks in general. Network design is not based on formal principles. The OS courses teach fundamental principles, but the teaching of computer networks is not the same. When you have an OS course, you have a lot of information about the principles, while in SDN, in networking, you have a big bag of protocols. So why networks are not designed based on formal principles. Networks at the beginning used to be very simple, so we have what we had before was a basic Ethernet IP. So the beginning of networking or networks were just wired LAN, local area networks, easy to manage. But as the time has evolved and the requirements also have become more, let's say, strict. So we have new control requirements. For instance, ACLs, ACLs that are for security, VLANs, to separate traffic inside the network, traffic engineering, middle boxes as firewalls, DPIs, WAN optimizers, so a lot of different functions inside the network. And this have led to bigger and bigger complexity in the network. Even if we have that, infrastructure still works. This is good. And this is only because of our great ability to manage complexity, but it's becoming every time more difficult. And this is a blessing and a curse, because even if it's easy, and not easy, it's possible to deal with this big complexity, is very difficult to innovate due to the complexity. So as it is very complex to configure or to manage, to do the network management is very complicated to innovate, to put new features in the network. So what is SDN? Well, what are the principles of SDN, software-defined networking? The idea is that we follow a little bit what was done actually in the traditional computing. At the beginning in traditional computing, we had machine languages without abstraction, very complex. So the first IBM, so you had to program it at very low level. It was very difficult. Then operating systems were created, and this is the first level of abstraction. So we had higher level languages with file system, with virtual memory, and it was it was easier for programmers to construct or to build programs, because then you have the operating system there. And now in the modern language, you have even more abstractions. You have object orientation, garbage collection. You have a lot of APIs or interfaces to reuse code, and it's even easier for programmers. So because you have more and more abstractions, the operating system was the first abstraction, and then on top of it, you can even abstract more to ease the work of the programmer. So every time abstractions simplify programming. Abstractions are the way to reduce complexity, and this is very important. So what happened in traditional computing? Before, at the beginning, we had vertically integrated, closed, proprietary, slow innovation, small industry. The first IBM mainframes back in the 80s, 1980s, 40 years ago, were really huge mainframes where you have the specialized hardware, the operating system, and the applications made by the same manufacturer, and all in the same box, right? So you had the hardware, and this operating system worked for just this hardware, and the application worked just for this operating system. And then as you increment the abstractions and the interfaces between the different layers, you increment the ability to innovate. So from this vertically integrated, we pass to an horizontal integration. So we have open interfaces. So here we have the hardware, right? But we have an open interface, so you can program this hardware from different operating systems, right? So in the same hardware, you can have Windows, or you can have Linux or Mac, or even you can have with virtualization a lot of, at the same time, a lot of operating systems using the same hardware, right? And then from the operating system, you also have interfaces which allow the applications to configure or intervene this operating system. So the application you can program an application. It can work in Windows or in Linux or in Mac or in the ones you want. They offer the interfaces for you to program. So then you're free to program in each operating system, right? So the idea is that we do the same in the networking world, right? Right now, what we have is routers, switches, firewalls, all this networking equipment that is vertically integrated. The hardware is used by just the operating system of the manufacturer, the Cisco, Juniper, or whatever, and the specialized features that they accept. So you can just configure what they have in their operating systems and what their hardware allows, right? So if they don't have one routing protocol implemented, you cannot put this routing protocol to work. So the idea is that we switch to horizontal integration. This horizontal integration, we have merchant switching chips, so custom hardware, right? Open interface. This open interface will be very important, as you will see, for new operating systems, or what we will call new control planes, right? So we can have different control planes or network operating systems, and then these control planes also have open interfaces for any application. So if you want to program a new routing protocol, you can program it here. So a new application, a new traffic engineering strategy, you can program it here, and so on and so on. So in this way, the integration of the different layers is horizontal. This is the basic aim of SDN, to transform what we have in traditional, let's say, computing environments or traditional networking environments to an open and programmable environment. So we have in SDN two networking planes. This is important, what we call the data plane and what we call the control plane. The data plane is where the processing and delivery of packets take place with the lock and forwarding state. Okay, the forwarding state is the state, the state information that tells the packet where to go or what to do. So what you arrive to a switch, the switch will look at the header of the packet, and with the packet header and the forwarding state, so let's say the switch table will say this packet should go to this port, this packet should be discarded, this packet should be stored in a queue, or any action, right? So this all happens in the data plane. The data plane is in charge of the processing and delivery of packets. In control plane, we have it's the one that computes this forwarding state. So it is the one that computes what the data plane should do. So for instance, here you have the routing algorithms, the traffic engineering, the firewall state, and it determines how and where packets are forwarded. So this is the intelligence of the network. It computes this forwarding state, and it tells the routers and switches the forwarding state so that the data plane knows how to do with the packet. Okay, it is implemented traditionally. Right now, it is implemented with distributed protocols and manual configuration. So what you do, for instance, in a Cisco router, you configure the Cisco router to work with OSPF as the routing protocol. This is control plane information. So the running of OSPF is an activity of the control plane. Okay, and then when the routing protocol knows all the routing paths and tell the routing paths to the forwarding tables, the action of delivering these packets using this forwarding state is an action from the data plane. Okay. So the data plane actually works very well because it has abstractions, what we call layers in the TCP/IP model or the OSI model, right? So we have a physical layer, right? A physical layer that is actually built on a data link layer, which is built on a network or IP layer of best effort global packet delivery that is built on a transport layer that can have reliable or unreliable transport protocols, TCP or UDP. It isn't, and this is built on a applications layer. So you have the responsibilities and interfaces between each layer. So the applications will rely or are built on the transport layer, right? That relies also on the best effort global packet delivery of the network layer. And this best effort global packet delivery relies on the best effort local packet delivery of the data link layer that also relies on the local physical transfers of bits of the physical layer. So as you see, here we have interfaces and different layers. So the data plane is already decoupled and already use abstractions, right? So it already works. The problem then is with the control plane. So which are the abstractions of the control plane right now? And this is going to be, we're going to talk about these abstractions of the control plane in the following video. We will see that traditionally we don't have abstractions in the control plane. And what SDN proposed is actually to have those abstractions in the control plane. Thank you very much, and we see you in the next video.